Welcome everyone to AURI Connects Webinar Wednesday, part of AURI Connects monthly online series featuring updates on the work that AURI is doing to foster long-term economic benefit for Minnesota through value-added agricultural products. I'm Dan Scogan, the AURI Director of Government and Industry Relations and your host for Webinar Wednesdays. The AURI Connects program is hosted by the Agricultural Utilization Research Institute in Minnesota. This program aims to actively engage all participants in the food and ag industry to improve competitiveness of producers, businesses, and entrepreneurs through ongoing, purposeful connections of resources and partners along the value chain, and increase knowledge of opportunities, technologies, and trends. Remember, this event is being recorded and archived and can be found at auri.org. Remember that you will be muted during our presentations, but you can send us your written questions through the Q&A portal on your screen. Today, we welcome Michael Reese to discuss the potential for green ammonia and its impact on agriculture in Minnesota. Michael has been the Renewable Energy Director at the University of Minnesota West Central Research and Outreach Center in Morris, Minnesota, since 2001. He's overseen the development of the Renewable Energy Program at Morris and has participated as principal investigator or project manager on more than $18 million worth of research and demonstration projects, including wind energy, biomass gasification, renewable hydrogen and ammonia, and solar energy systems. Reese is also leading the Renewable Energy Program's new strategy to reduce fossil energy consumption in agricultural production systems through incorporating renewable and efficient energy technologies. He has addressed numerous national and regional conferences on the topic of renewable energy. So Michael Reese, welcome to Webinar Wednesday.
Thank you, Dan. And thank you to AURI for allowing me to present during AURI Connects. With that, I think we'll jump right into the presentation. So the topic today, as Dan mentioned, is green ammonia's future in Minnesota agriculture. I'm located at the University of Minnesota West Central Research and Outreach Center. We're one of 10 research and outreach centers across the state. We're located in West Central Minnesota near our sister campus of the University of Minnesota Morris. We're an 1,100-acre agriculture experiment station, and we have primary research areas that include agronomy, soil science, dairy, swine, horticulture, and renewable energy. As Dan mentioned in the introduction, our program goal is to reduce fossil energy consumption in production agriculture. About 20 to 25% of greenhouse gas emissions in Minnesota and the world are attributed to agriculture, forestry, and related industries. And 1% of the global greenhouse gas emissions are attributed to ammonia and nitrogen fertilizer production. Markets and policies are trending toward the need for reducing greenhouse gas emissions in production agriculture. And we have a number of research initiatives underway to address these, ranging from crops and livestock and dairy and swine and other areas as well. I'd like to acknowledge some of the support that we have received through the years to develop our initiatives, including from the Legislative Assistance Commission on Minnesota Resources and Environmental Natural Resource Trust Fund, MnDRIVE, the U.S. Department of Energy through their ARPA-E refill program, and others as well. So our topic today is green ammonia. University of Minnesota is a global research leader in this field. In 2013, we established the first in the world wind-to-ammonia pilot plant at our facility, where we use wind energy to electrolyze water, pull nitrogen from the air, and combine them together to form anhydrous ammonia. And if you look at the diagram on the right, you see the anhydrous ammonia molecule. And then on the left is where our pilot plant is located at a research farm, where we also have co-located two 1.65 megawatt wind turbines and quite a bit of solar PV as well. One nice thing about ammonia is it has some flexibility that you probably don't hear much about other than nitrogen fertilizer, and I'll talk about that in the coming slides. Here's a picture of our pilot plant located at the Research and Outreach Center near Morris. We bring power in from 1.65 megawatt wind turbine. We use that power, again, to electrolyze water in the buildings in the background. We pull nitrogen from the air. We separate those two. We store it in the tanks in the foreground. The green tanks are for nitrogen. The red tanks are for hydrogen. And then we combine those together to form anhydrous ammonia, and then store it in the ammonia production storage tank in the foreground. We also have ammonia pump and loadout facilities, so we can fill nurse tanks or tanker trucks as well. And this is a relatively small pilot plant. We can produce about 6 pounds per hour with this plant. Green ammonia is, I think, is an elegant concept where you can take wind energy, water, and air to produce nitrogen fertilizer and use on the ground soil below the wind turbines. And when we first began working in renewable energy and looking at installing a large-scale wind turbine, we ran across some of the same problems that other developers ran into: limited transmission capacity and utilities that were having difficulty managing variable nature of wind and solar PV. Wind mostly is generated in the evening when there's low load, and then in seasons where there again is lower load requirements. So the idea is that the question is, how can we monetize wind energy and make a product that we can market in Minnesota and across the Midwest? So in this process, we're again electrolyzing water. We're separating nitrogen from air. So we're removing the oxygen and argon in a molecular sieve. And then we're using the hydrogen and nitrogen gas in a traditional or conventional Haber-Bosch process. Wind and solar can also, intermittency can pose a problem for Haber-Bosch processes. So we have looked at technology to mitigate those issues, and that includes managing these through advanced process controls, additional hydrogen and nitrogen storage, thermal integration storage, and lower pressure and temperature production processes. And heat loss is a primary challenge for restarting the process. If you look at why green ammonia makes sense for the Midwest and the US in general, is if you look at the left side of the screen, the picture displayed is the wind resource across the United States. And you see through the central portion of the United States, huge wind resources that we really haven't tapped at this point in time to the degree that we could. On the right side of the screen is the map of the highest corn producing counties in Minnesota, or excuse me, in the Midwest. And if you see this green arc, the dark green represents the highest producing corn counties in the US. That's essentially the Corn Belt. And the reason why I put this map up is that corn is one of the largest users of anhydrous ammonia. And so when you overlay the wind resource with the demand for anhydrous ammonia, you see a nice synergy. And this is just for fertilizer. We'll talk a little bit more about using anhydrous ammonia for energy as well. But overall, wind resource is synergistic with Midwest corn production and nitrogen fertilizer demand. It's inherently distributed. So you think of small scale or moderate scale ammonia production facilities that could be located in the Midwest where we have the renewable energy as well. US nitrogen fertilizer demand could be met with approximately 50,000 megawatts of nameplate wind energy capacity, and current US wind generation is 105,000 megawatts of nameplate capacity. So for not too much more, we can meet all the nitrogen fertilizer demands in the US using renewable wind and solar power. There's an opportunity to utilize stranded wind and solar resources and excess nuclear power to do this. And new technology policy is needed for green nitrogen fertilizer to compete. In the near term. So why green ammonia and why now? As I said, we've been working on this since 2013 with our pilot plant, and actually before that, since 2003 timeframe, developing the system. There's essentially a convergence of three primary factors. There's an increased motivation on a global basis to address changing climate. current nitrogen fertilizer production is responsible for 1% of all global greenhouse gas emissions. Policy investment dollars are moving towards technologies and companies that support lowering greenhouse gas emissions. The second reason is there's a financial motivation to store low-cost intermittent renewables and excess nuclear power caused by increased renewables on the grid. And at times, wind can be 1 to 1.5 cents or lower in pricing on the grid, and so it makes sense for processes that enable us to take advantage of those low-priced renewables. Then there's a realization, I believe, that ammonia is one of the best and perhaps the best option to store and transport hydrogen, which could be important from a energy storage standpoint, but also as a fuel for transportation. And when we talk about fuel for transportation, I think overall we're moving more towards electric vehicles, but there is also a niche for larger scale transport, such as rail and marine applications, where ammonia might fit well. So there's been a lot of news about hydrogen, green ammonia recently. We've had our share as well, but what some might not realize is that the amount of activity happening across the world with green ammonia, companies such as Siemens, so major corporations worldwide, are looking at green ammonia to meet challenges of the 21st century in terms of greenhouse gas emissions for agriculture, as well as meeting fuel requirements or green fuel requirements worldwide. This Business Wire publication indicates that in 2019, there was $17 million US dollars invested in green ammonia, and they're projecting by 2030, they expect 852 million, which is a 55% increase during that period of time. And most of this is expected to be for power generation segments using ammonia for energy storage. And that actually might be a light or a very conservative estimate. You see other companies looking at ammonia, green ammonia. There's an Air Products project in Saudi Arabia, a $5 billion green ammonia hydrogen project. Green ammonia is being looked at for marine applications worldwide and other interesting activities related to green ammonia. I think it's also important to note that most, if not all, the world's leading ammonia production, engineering, and technology companies are working on zero carbon ammonia. And not only for fertilizer, but also they view it and others view it as an opportunity again for transportation, fuel, and as well as energy storage. So I'm going to talk a little bit more about green ammonia for fertilizer. In Minnesota and across the Midwest, we have a robust infrastructure for ammonia. Again, we use it for nitrogen fertilizer. It's our primary source of nitrogen fertilizer. Currently, ammonia is produced in the United States primarily from steam methane reforming of natural gas. There is some coal production of ammonia as well, but then it's transported through various means, pipelines, barges, rail, and tanker trucks to regional facilities for storage, and then brought out to local cooperatives or egg input centers where it's stored and then put into nurse tanks, and then farmers bring the nurse tanks out to their fields and inject it, similar to what you see in the bottom picture on the right side. So we have a robust infrastructure for green ammonia. I think it's important also to point out that anhydrous ammonia is the basis for nearly all nitrogen fertilizer synthesis. In the market's roughly $6 billion. Minnesota farmers spend between $500 and $800 million per year in nitrogen fertilizer. And then, I believe that farmers could participate in ownership of green ammonia production as well. If you look at the table, you'll see that the various types of nitrogen fertilizer that Minnesota farmers use. Actually, these are essentially the major fertilizers, all the major fertilizers they use. Anhydrous ammonia, urea, which is made from anhydrous ammonia, urea ammonium nitrate, which is 28% liquid, and then monoammonia phosphate and diammonia phosphate as well. If you look at across the US, the amount of nitrogen fertilizer that's consumed, if you look at corn, we have close to 8 million tons of nitrogen fertilizer. In soy, not so much anhydrous ammonia, but other forms of fertilizer. We have close to 750,000 tons. Wheat, 1.7 million tons. Cotton, close to 500,000 tons. And what that ends up to equal is about $6.2 to $8.1 billion in the US each year is spent on nitrogen fertilizer. So if we look at nitrogen ammonia's role in corn production in Minnesota and the Midwest, approximately 1.6 megajoules of energy is consumed to produce 1 kilogram of corn. And my colleague Joel Tellickson at the University of Minnesota West Central Research and Outreach Center looked at the fossil energy footprint of corn production at our center and, and has come up with the following pie chart, identifying where the energy footprint is. If you look at the black portion of the graph, that is nitrogen fertilizer. So of the total footprint, almost 37% of that footprint is related to nitrogen fertilizer. And then if you look up above, I think importantly, I'll bring it up later, 42% is related to grain drying. Now this might vary some across the Midwest, but the idea is generally the same, that we're using tremendous amounts of fossil energy for nitrogen fertilizer and for grain drying. And then field work or tractors, is about 14%. So roughly a third of corn is used for ethanol production and 2/3 for livestock and some export. And this will be important in the next slide. In nitrogen fertilizer ranks the second highest again, and has a significant impact on the carbon intensity of corn grain as well as other ag products such as ethanol. So if we were going to look at green ammonia, there's potential to reduce the fossil energy footprint of corn production nearly 90%. And you might say, well, how can you do that if you're just replacing fertilizer? Well, we have projects underway researching the use of anhydrous ammonia for grain drying, as well as use for fueling tractors as well. And if you could develop a system like this, a colleague of mine, Matt Pallas and Prodromos Steatidis, have shown that the emissions avoidance cost of such a system would be about $18 a ton for CO2, which is extremely low. There's other possibilities for anhydrous ammonia, one of which is to use it for energy storage and sector coupling with agriculture. And so kind of switching gears to talk about using ammonia as energy storage. From an electric grid standpoint, ammonia could provide both distribution and transmission scale energy storage. There's a wide range of fuel uses. It can be used in internal combustion engines for generators. It can be used in gas turbines, fuel cells, vehicles, marine or shipping, the shipping industry, the rail industry, and it can also be used for thermal energy. There's seasonal storage capability, and I think this is the greatest strength of, we have shown that it's the greatest strength of green ammonia, and ammonia is being able to store it for long durations of time. It can be used for grid stabilization. It's readily dispatchable generation capacity, and it's synergistic with the ag industry because peak load and peak fertilizer months are complementary or during opposite seasons. It enables utilization of excess generation of wind, solar, nuclear power, and low and negatively priced power within the system. Provides emergency backup outside of traditional energy sources. This was important during the polar vortex that Minnesota and the Midwest experienced a couple years ago, and could be important in the case of, for example, Texas and their issues this past winter. Typically, we have large amounts of anhydrous ammonia stored in the wintertime, and that could be used for energy when needed. There's flexibility between renewable and non-renewable generation. Again, we already have a large and robust ammonia infrastructure, many tons of storage across the Midwest. And there is really no difference when it comes to generation, whether it's brown or conventional produced ammonia or whether it's green ammonia. Ammonia is ammonia. So we have this opportunity to use both if needed. Again, there's significant levels of ammonia storage already in the Midwest, and it's usually near distribution and transmission lines, so it would be relatively easy access if you had a generator nearby. And then another interesting part about ammonia is there's multiple avenues of synthesis. You can make ammonia with green electricity. You can make it with methane for manure through anaerobic digestion. You can use biomass gasification to make ammonia. So many different routes, and I think moving forward, it might be best to pick, not to pick the technology, but to allow the economics to pick the technology that makes the most sense. This is a picture of our ammonia production skid, and this is a conventional Haber-Bosch process that we installed at Morris. What we found is that it's not efficient enough at scale, at the small scale, to compete against conventional natural gas-based ammonia production. So we teamed with researchers at the University of Minnesota Department of Chemical Engineering Material Science to develop new technologies. And Alan McCormick, Ed Kussler, Lanny Schmidt, Prodomus Deotitis, and others developed a patented process that we term absorbent enhanced ammonia production. Typically, ammonia production system takes high pressure and high temperature hydrogen and nitrogen, moves it through a reactor and catalyst, and the result is about 20% anhydrous ammonia, and that's chilled, and then ammonia becomes a liquid and is separated from the rest of the gases. Now when people try to improve this process, many focus on the reactor and the catalyst, trying to get higher yield. In our case, we focused on the separation process. So we removed the condenser, which you see as identified in the blue in the diagram, and switched to absorbent. So we're taking salts and we're absorbing ammonia as it's being produced. And then we can do that under lower pressure, lower temperature atmospheres. What results is a lower capital investment, about 40%. We do have some higher energy consumption, but we haven't integrated the thermal portion of this process yet, so we believe that could be improved. And then overall, this process is less expensive at smaller production scales. The graph essentially shows that if you look at the light green bar versus the dark green bar, light green is condenser based, dark green is absorbent enhanced. And so the absorbent enhanced can win out at smaller scales, but is essentially closes to the same, is close to the same at higher production scales that you traditionally see at a conventional, large scale conventional ammonia production facility. The point is that again, we expect that there might be small or moderate scale ammonia production facilities near renewable energy production or wind production facilities. So typically they would not be as massive a scale as what we now see in the natural gas production of anhydrous ammonia. So my colleagues Matt Pallas and Prodomus Deotitis did a study looking at the use of anhydrous ammonia for energy storage. They looked at 15 different cities across the US and used data from these particular cities. They've added in, the model that they used would add in wind turbines or solar PV as needed and energy storage as needed. And each time the model chose both anhydrous ammonia and hydrogen as the best source of energy storage. And the reason for that is that the combination gives the lowest cost. Hydrogen is good if you're using it short-term, on a short-term basis. Ammonia comes in when you're storing it long-term. And so the reason for why ammonia is better long-term is that it's lower cost storage. Hydrogen is very costly to store. And so you want to use that as it's being produced, perhaps 8, 10 hours, 12 hours from when it's produced, use that to generate electricity. If you can't generate or don't need the hydrogen at that point to generate electricity, you use it to produce anhydrous ammonia. You might wonder about, well, where do batteries fit in on this? And in this case, I'm just comparing Minneapolis, Denver, and Amarillo, Texas. And both hydrogen and ammonia beat, in the combination, beat out batteries each time. Batteries are extremely expensive, even though there might be an application for that short duration time when you need instantaneous power definitely for seasonal storage. They're not competitive with ammonia in the case of this study. This slide shows some of the breakdown of the costs, and if you look at the levelized cost per megawatt hour on the y-axis, one thing to note is that the renewable generation systems were also included in this. The actual cost of the energy storage is very small, with ammonia production being $11 to $16 per megawatt hour. So we're talking a fairly small amount of dollars to store green ammonia or renewable electricity. The same study they looked at, same study they also looked at generation, production of hydrogen, production of anhydrous ammonia, which is the top bar, and then the power generation using each in the middle bar. And that just shows when the generators and when the fuel is being used. The maroon is hydrogen, the gray is ammonia. The top bar actually shows the best why it's important to have anhydrous ammonia from a long-term storage standpoint. You're able to, again, store it long-term. And then the bottom is the power generation from Minneapolis. Or excuse me, the power load. So another study again looked at coupling agriculture as well as energy storage, using ammonia for fertilizer and tractor and grain drying, as well as producing electricity when needed. And this study actually looked at sector coupling, bringing the two industries together, and again resulted in an emission avoidance cost of $18 per ton of CO2. So a colleague of mine in the Department of Mechanical Engineering, Mechanical Engineering, Will Northrup, as well as a colleague in University of Minnesota Duluth, Mechanical Engineering, Allison Hoxie, have been looking at using ammonia in tractor fuel and for grain drying and other applications. We believe that it's a good fuel. There's some issues that need to be overcome, and some of the technology that Will has developed has mitigated some of these issues. One of the technologies is a thermal reformer. Oh, don't have a picture of that, but a thermal reformer that basically cracks a small portion of the ammonia into hydrogen. So when you are combusting it, either in a tractor or for grain drying, it's not just a pure ammonia. It's a combination of both hydrogen and ammonia, and that resolves many of the issues. So if you look at the cost of producing green ammonia, I think there's a very wide variety of green electricity pricing out there. Recently, contracts between utilities and wind developers have been in the 1 to 1.5 cent range, and if you look at those numbers, we're getting very close to being cost competitive with conventional ammonia retail prices, at least. We're close to $400 a ton, and right now retail ammonia is close to $550 a ton. So I mentioned large-scale ammonia storage. The picture that I'm showing here on the left is the CF Industries Glenwood Ammonia Terminal. It's a refrigerated ammonia facility with a capacity of 60,000 tons of ammonia. That's equivalent to production of 111,000 megawatt hours of electricity. And there's wind and solar PV in close proximity, and CapEx 500 kV line in close proximity. So this essentially could be a hub for wind energy transmission. If you look at the map, the green lines represent, the dark green lines represent the CapEx transmission that was recently built out in Minnesota and across the Midwest. And the yellow stars are where these large ammonia storage facilities are located at. So essentially the idea would be that wind coming from western or southwestern Minnesota or the Dakotas could be stored at these facilities and then the ammonia could be used later to generate electricity as needed, or it could be used for thermal energy in the case of, as I mentioned, like a polar vortex or something along those lines. If you look broader across the region, you see quite a bit more of ammonia energy storage, particularly in northern Iowa. And so I think this is an untapped opportunity for utilities to consider moving forward. We've been working on green ammonia since 2005, and we've developed some technologies at the University of Minnesota that we think are attractive. As part of that, we worked in a refuel program through the U.S. Department of Energy to further develop that technology. And we started collaborating with other participants in the refuel program. And we recently proposed to the U.S. Department of Energy ARPA-E refuel program to develop a large-scale demonstration project producing 1 metric ton of ammonia per day, utilizing the best technologies that were developed in this refuel program. And so we proposed a project team that includes the University of Minnesota, be led by the Research Triangle Institute in North Carolina, as well as some common names such as GE Electric and Shell, Nutrien, and utilities such as Xcel Energy, REA, and Otter Tail Power. And so we believe we have a good team put together to develop and demonstrate the latest and most advanced ammonia production, green ammonia production facility in the world. And so please stay tuned for more information to see if that funding is received. That project will be a 3-phase plan for technology de-risking. And it includes design optimization, building a pilot plant, and then demonstrating that pilot plant as well. So in conclusion, the agriculture industry should play a significant role in green ammonia production and utilization. Conventional nitrogen fertilizer production represents approximately 1% of all global greenhouse gas emissions. So moving forward, I think we're going to see significant pressure worldwide to make changes in that area. The carbon intensity of grain, meat, milk, ethanol, and other ag products is highly influenced by conventional production of nitrogen fertilizer. More and more, we're going to see that the push from consumers and consumer groups to lower the carbon intensity of our agriculture products. And so green ammonia is one of the cores to that. If you look at green ammonia compared to other technologies, green ammonia is a drop-in replacement for nitrogen fertilizer right now. So that's the nice part about it, is not as disruptive as some of the other potential scenarios where we're reducing carbon intensity of these products. Distributed nature of renewable electricity generation favors regional production of green ammonia over centralized plants. Coupled with the declining costs of wind and solar generation, green ammonia production technologies are becoming cost competitive. And green ammonia presents significant value-added agriculture opportunities via multiple synthesis routes and sector coupling moving forward for Minnesota. So moving forward, we're working on our pilot and demonstration projects with the refuel program. Others are needed. Encourage those of you interested in trying to move forward in this area. Education, organization, and advocacy is needed as well. And perhaps some of that is being covered by the Hydrogen Economy Consortium, which is being led in part by efforts of AURI. Green ammonia certification tracking is required. MRETS is looking into this, as well as others across the U.S. And state and national green ammonia policy could be used to encourage development of a promising industry. And I like to just put a plug in that I think in this case that some ethanol-like policies might really stimulate this industry. So green ammonia is ready for the next step. Minnesota can continue to play a leadership role in this emerging industry while creating new business and jobs. And how will Minnesota position itself moving forward? I think that question is yet unanswered, but hopefully we'll be taking advantage of this new emerging industry. So with that, I'd like to thank you for your time. I put in some resources in this presentation. I'd like to thank my colleagues, Ellen McCormick, Perdomo Steatitis, Matt Pallas, Chi Zhang, Jeff Schott, and Will Northrup, Allison Hoxie, as well as Samir Parvathikar at RTI International. And my contact information is there as well. So with that, I'll open it up for questions.
All right, Mike, thank you very much. Great presentation. I think it's the third or fourth time that I've seen it, and always enjoy walking through that. And it seems to always generate some additional questions as I watch it. And you've certainly stimulated some questions from those who are participating in our webinar today. Let's go to a three-part question here to get us started. What's your source for water? Is there any waste from the process that's being described? And he added that perhaps I missed it, but what is the greenhouse gas life cycle for green ammonia versus conventionally sourced or produced ammonia?
Okay, so the first question, what is the source of water? We use well water. It has to be a pure form of water, so we deionize it as well. And so there is some wastewater associated with that, not much. If you're familiar with farming, typically we use 10 to 15 gallons per acre for each pass with a sprayer to spray chemicals on, whether it's some type of pesticide. And in this process, we use about 15 gallons an acre as well, roughly, or less than 15 gallons an acre. When an irrigator goes around in field, you're applying close to 1,000 gallons per acre. So fairly small amount of water used in this process compared to other processes. The second question was what waste. I mentioned the water waste already. I would say that there's byproducts that could be captured. In a larger facility, you might take a look at capturing oxygen, but really, we're essentially pulling nitrogen from the air, so we're releasing the oxygen and argon from air. So we're just releasing it back into air, and then we're electrolyzing water, so there's an oxygen source there as well. And so that might be one you would want to capture moving forward. And you have to remind me, Dan.
Third part of this question, Mike, was the GHG life cycle for green ammonia.
Sure, it's considerably better than the conventional process. It depends on what you're using. If you're using wind and solar, it's going to be many times better. It's a multiple better than conventional ammonia production. If you're using biomass or anaerobic digestion, it won't be as great, but you still have a significant added advantage with green ammonia versus brown or gray ammonia.
An organic question: how can we use green ammonia sources in USDA organic farm production? As you know, that is an entirely complex set of requirements. However, organic production is what is currently the most lacking in good nitrogen sources.
I would agree with you. I would agree with the questioner there. The Research and Outreach Center is a organic certified farm. We grow organic crops for our organic dairy, and we cannot use green ammonia to supply nitrogen to those acres. And I think it's a certification process. But if you're looking at green ammonia, there's still potential impact to the soil biology in terms of earthworms and other organisms within that soil structure. I think if I was looking at certifying nitrogen fertilizer made from green ammonia, I might consider going to urea or another form of nitrogen fertilizer that may not have those same issues. And then I think you'd have a good case to be made for the certifying bodies for organic crops and as well as organic dairy and other organic types of food.
Questioner asks, so is the thinking for production somewhat akin to the distributed generation for electricity? Is it?
I would say that in our modeling, we're looking at more of the ethanol plant size, the 3-county, 4-county regional production facilities. I think there's opportunities for smaller scale and smaller size ammonia production facilities with advancement in technology. But I think initially, to get this industry up and running, we need to have that scale. And we're probably looking at 100 to 150 megawatt consumption of or nameplate capacity wind farms at that scale.
Toward the end of your presentation, Mike, you showed that ammonia is so versatile in many different ways. Why do you think it's lagged so much in being brought forward?
I just don't think that there was a full first of all, the technology needed to be advanced, and that's what this refuel program has done through the Department of Energy. U.S. was actually slow into this area. Japan, Australia, Europe have put millions of dollars into research and development, and have found the technology that works. I think overall, though, we've heard batteries and we've heard other forms of energy storage. So I think we're focused on that. I like to say that ammonia, for those of you old enough to understand this, that ammonia is the Rodney Dangerfield of energy storage. For a long time, it didn't get any respect, and until this technology was developed and people started to understand that that batteries are expensive. So looked at hydrogen. Hydrogen is difficult to store, and now we have ammonia. People were concerned about the safety of ammonia, but it's the second most transported chemical in the world, and so we have the expertise and experience in handling it safely. And so I think that's the primary reasons why it's come about and gained interest now.
Well, and you brought up safety, and we do have a question around safety, so let's go to that one next. Please speak to the safety concerns with storing and using ammonia as a fuel, especially in a population center.
Yeah, well, there definitely is safety concerns with ammonia, and that's in the farming communities, we understand that very well. One of the concerns, though, with ammonia is the transportation. So if you're using rail, for example, or barges from the Gulf Coast or from Canada, bringing it to the Midwest, there's a lot of risks associated with rail going through urban areas and barges going through urban areas with ammonia. But if you're producing it locally or regional, some of those risks are mitigated. You don't have as far to transport it. From the standpoint of, well, we want to have hydrogen for vehicles in downtown Minneapolis or in an urban area, well, I think that's a concern, and we're actually working on technologies for inherently safe ammonia storage. So being able to store ammonia so that if there's a leak, it actually won't be, it won't have an impact. It would actually be held within this material, and you would have controlled release when you wanted it. So I think there's technologies that are coming about to make this much safer and lower the risk in urban areas.
Short of corn being a biomass for the production of ethanol and co-products, do you see any point of intersection with ethanol per se in the overall system that you outlined here today?
Well, I see a couple different intersections. First of all, we want to lower the carbon intensity of ethanol. And so one of the best ways of doing that from a farmer standpoint is to use green ammonia. It's a drop-in replacement. You can just drop it into your current processes. The second part is, some of the discussion has been, well, again, with ammonia, green ammonia, you can produce other forms of nitrogen fertilizer. One might be urea. So rather than just having the carbon dioxide, carbon monoxide go up the stack, capture that carbon source and combine it with your ammonia to form green urea. And so there's an opportunity there. From a green hydrogen standpoint, I think there's opportunities with ethanol as well. Whether you're talking renewable natural gas production, ethanol production was from carbon dioxide, or urea production, you need green hydrogen to do all of that. So if I was in the ethanol industry moving forward, I'd be taking a look at green hydrogen production technologies and using green electricity or something like that to power the plant.
Michael, someone was interested in that hydrogen consortium that you mentioned in your presentation. They were wondering what the name of that group was.
Yeah, it's actually, it's just being formed. The name has been discussed, and right now I think they've settled on the Hydrogen Economy Consortium. And so you can contact Dan. I think you'd be a good contact, or Rod Larkins at AURI, or NDSU, and there's a lot of, you can contact me and I could get you in direct contact with the organizers of that organization.
Participant today was interested to hear about the new pilot plant plans and how it would be they're curious how it would be powered, and do you foresee any electricity capacity troubles or possible troubles?
It'll be powered using wind energy and solar PV on site or on our distribution or feeder line. And so no, we don't see any issues with the amount of power that we'll be providing to that plant at this point in time.
And then would you elaborate on the 110 megawatts of electricity at the Glenwood storage site? Was that part of your?
Sure. If you just look at the amount of ammonia capacity that can be stored at the Glenwood refrigerated ammonia facility, that would translate to roughly 110 megawatt hours of electricity production. So, point is, there's a large volume of storage capacity, of which is used right now for nitrogen fertilizer. So in many respects, it's essentially underutilized. If we were to use it for both fertilizer as well as energy storage, there'd be more throughput of ammonia throughout the year. And so I think that's what anyone wants most likely, is more use of facilities to spread the costs over larger activities and things of that nature.
I was going to ask you an economics question, but we do have a question from a participant today that says, how do you anticipate the distributed scale production, either co-op or regional, costs and how they will compare to large scale costs when this technology is mature?
Sure. Well, like I said, I showed one of the slides that indicated we're basically at retail price right now with the technology. If you add in any kind of carbon tax or green ammonia incentive, I think we're competitive at that point in time. If you think of the ethanol industry, farmer-based ethanol plants, initially people would have said, well, those can't be cost competitive. But yes, they can be cost competitive. And what happened was the policy carved out a market for them and enabled the industry to grow and become strong. And so that's probably what's needed for green ammonia if you're going to make that work out. Need to carve out a market, need to have some incentives, need to have some experience in operating these plants. And then at that point, they can stand on their own and be competitive.
Well, Michael Reese, that concludes our list of questions and our presentation today, but I'll give you the last word on this subject. What do you want the people to remember as they leave today?
I would like everyone to remember that there's opportunities using green hydrogen and green ammonia moving forward for agriculture. I think it's transformational when we can lower the fossil energy footprint of our products, corn, small grain, meat, milk, ethanol, and do it in what's essentially drop-in capacity, being able to drop in a green renewable product right into our current production systems.
Very good, Michael. Thanks for your time.
Thank you very much.
And that concludes AURI Connects webinar Wednesday for today. We do want to thank Michael Reese for his time and for his presentation. AURI Connects Webinar Wednesday is presented by the Agricultural Utilization Research Institute of Minnesota. AURI's mission is to foster long-term economic benefit for Minnesota through value-added agricultural products and processes. And we are interested in your feedback, so please respond when we send you our event evaluations. Remember, for more information on today's program or any of the work that AURI is involved with, you can go to auri.org. And then join us on May 12th to hear from AURI team members in Waseca, Minnesota, as they highlight their lab capabilities, which support renewable energy, co-product development, bio-based products, and food projects. This virtual event will showcase new resource additions to the AURI Waseca pilot lab, such as food-grade processing area, hemp fiber decorticator, a new drying and dewatering capability, and densification equipment, and more. We'll be hearing from Al Daring, the senior scientist of co-products at AURI, from Riley Gordon, the AURI engineer, and from Abel Takeski, the associate scientist in co-products at AURI. We'll also learn how AURI has multiple facilities across the state of Minnesota that offer a broad range of services, from hands-on technical assistance to research services and a targeted network of resources. And it's all coming up on Wednesday, May 12th. You can always learn more about other work that AURI is involved with by going online to auri.org. We'll see you May 12th for another AURI Connects Webinar Wednesday.